All right, guys, we're going to be reviewing limits in this video. This is not like our regular videos where I do example problems and then let you practice after I explain the concept. Basically, I'm just going to do a quick rundown of all the concepts that have to do with limits. We're going to be getting all of our practice in throughout the week in class. So this is just going to be a nice little resource for you guys to have as you are doing those problems, and also a nice little resource to have as a study tool for your AP exam that's coming up shortly. So make sure you do take good notes and fill in the blanks as we go, because your handout there will have a few blanks. Let's go ahead and get started here. So first of all, let's talk about what a limit is. A limit is the y value that a function approaches as the x value approaches some number. So let's say that x is approaching c, then the y value that we're getting closer and closer to as that happens is the limit. Okay, and so that's what a limit is. Now, limits can come from the right side or from the left side. If it's from the left side, then you're going to have a plus here. If it's from the left, if it's from the right, you'll have a plus sign. If it's from the left, you'll have a minus sign. So let me give you guys a quick little graph here just to kind of illustrate the concept. Let's say that this is x equals 3, and then let's say that there's a dot here, and my function looks something like this. And let's say that y value up there is about, I don't know, we'll just say 6. So as I approach the x value of 3, what y value am I getting closer and closer to? I'm getting closer and closer to 6. So the limit here would be 6. All right. Now we have the left-sided limit and we have the right-sided limit, and they happen to meet up at one point. And so in that case, we would say that the limit exists. Okay, but there are situations where they're not the same. Okay. A limit may fail to exist if the right-handed limit and the left-handed limit don't match. So an example of that would be something like this. Suppose I was approaching this x value of 3 here, and as I came from the left, we were getting closer and closer to a y value here. Let's say that's 1. But as I approach x equals 3 from the right side, I'm getting a different limit. Let's say that's like 5. In that case, that would be an example where the right-handed limits and left-handed limits don't match, and therefore the limit does not exist. Okay, or a limit could equal infinity. That's another situation that we want to be cognizant of. In those cases, and I would be adding these pictures, by the way, to your notes. All this stuff can be helpful, but I'm running out of space, so I'm going to erase and start afresh here. But this is called an infinite limit, when the limit is equal to infinity. And what that looks like is, let's say I'm approaching 3, but as I get closer and closer to 3, the y value just kind of shoots up into infinity. That would be like a positive infinity because we're going in an upward direction. But if you're approaching 3 and it shoots downwards, that would be like a negative infinity. And those are usually associated with vertical asymptotes. It's like your graph can never touch that line. It's an invisible force field. It can get closer and closer to it but never reach it. But as it gets closer, it gets either higher and higher or lower and lower, and those are infinities. And so these are also limits that fail to exist. So we have a limit is the y value that a function is approaching as x approaches a number, and that's from the right and from the left. And that's the only way that a limit can exist, is if the right-hand limit and the left-hand limit are the same. If they're not the same, then you have the limit does not exist. Or if you have a vertical asymptote, you get infinite limits. And in those cases, the limit doesn't exist either. So that's what a limit is in short. A third situation where a limit may fail to exist, which is a little bit more rare, is if the function is oscillating. I'll give you an illustration of that too, but these are kind of rare. They're not really, common to see. But let's say that as I approach 3, my graph is going up and down, but as I get closer and closer to 3, it's oscillating faster and faster. When that happens, it never really reaches a number. You could zoom in forever, and what's going to happen is as you get closer and closer to 3, it oscillates faster and faster, and by the time you get to 3, you're just never really able to get there. It's just constantly going back and forth. So that's another kind of situation. Those are pretty rare, but they are a thing. They happen a lot with trig functions. All right. So another concept I want to review with you guys is the concept of continuity. All right. So let's say that the limit of a function actually exists. So let's say I am approaching a point from the left and I'm approaching a point from the right. Okay. In that case, the limit exists. And if the function itself also exists, in other words, there's actually a dot there, the function is actually defined, that's another requirement. The function has to exist and the limit has to exist, and most importantly, they have to be the same thing. In other words, the dot I approach from the left and the right has to be the same thing as the solid dot that's actually there. There are some cases where that doesn't happen, and when that's the case, we have what's called a discontinuity, which is what our next slide is all about. So let's talk about types of discontinuities. And this is going to be an important slide for your FRQs. Let me slide down here a little bit. So you can see that little note at the bottom. These reasons that I'm going to be giving for you on these are useful for FRQs. A lot of times on FRQs, they ask us to give a reason why a function may be discontinuous. And so I'm going to show you how to write that using limit notation, and that writing is useful for FRQs. So something that you want to be aware of. Now there's two kinds of discontinuities. There's removable discontinuities and there's non-removable discontinuities. So let's talk about the removable ones. Those are ones where the limit actually exists. Okay, so one example of a removable discontinuity is when you have a hole. In this case, as you're approaching from the left and as you're approaching from the right, we are approaching the same point, and so the limit actually exists. But there's a hole there. Now, the reason that we would give for that is we would say that f of some number, we'll call it c, does not exist. Okay, so the function doesn't exist. The limit exists, but the function doesn't exist. And therefore, it's not continuous. Because remember, for something to be continuous, the limit has to exist, the function has to exist, and those two things have to be the same. So in this case, it's a discontinuity because the function doesn't exist. However, it's a removable discontinuity because the limit does exist. All right. Another way that a discontinuity can be removable is another hole situation, but it's got a little bit of a different reason associated with it. So let's say the limit exists. And let's say that the function exists also. It's just that the black dot, in other words, the place where the function actually exists, is not the same thing as the open dot, which is the limit. Okay, so in that case, you would say that the function's value at c is not equal to the limit of that function as x approaches c. So even though both the limit and the function exist, the problem is that those are not the same thing, and therefore it's a discontinuity. Now, to give you guys a more basic understanding of what continuity is, continuity just basically means if I have point A, say you don't need to write this, but let's just say I'm at point A and here's point B. If you can get from point A to point B without having to pick up your pencil, then that line is continuous. So as you guys can see, if there's a hole there, if I'm drawing this, I would have to pick up my pencil to go across that hole, right? So anytime you have to pick up your pencil, then you have a discontinuity. Okay, so that's what a discontinuity is. So we've talked about one type, the removable ones. Those are ones where the limit actually exists. And you could have removable discontinuities if the function doesn't exist or if the function just doesn't match the limit. All right, and those are removable discontinuities. Let's talk about, and make sure you guys are writing these notes down as we go. And by the way, this right here, this is the stuff that I was saying you want to make sure that you know how to write that. Okay, that's good stuff for FRQs. All right, let's go ahead and take a look at the second type. We have non-removable discontinuities. These are discontinuities where the limit does not exist. Okay, so one type of situation we've already seen on our lesson today is a jump. Okay, so in that case, the limit from the left is not matching the limit from the right. They're at different heights, and therefore they have different y values, and therefore the limit does not exist. So we call those jumps. So the way that you would say that the reason you would give for the limit not existing here is you would say that the limit as x approaches whatever number you are doing from the right is not the same thing as the limit as x approaches that same number from the left. So that would be the reason for those kinds. So if you ever come across a picture where they say, why does the limit not exist here? You would say, because of this situation, okay? The only difference is instead of a c, you'll actually have a number there. It depends on what x value you are approaching, all right? So that's one type of limit that does not exist, and therefore a non-removable discontinuity. Another type of non-removable discontinuity is a vertical asymptote. So for that, I'm just going to draw a dotted line like that. And as we approach, it doesn't matter whether it's going up or down. In those cases, basically, the function just doesn't exist. So you could say the limit doesn't exist because it doesn't, or you could say that the function doesn't exist. It doesn't really matter. I guess we'll just say that the limit as x approaches c does not exist. But you could also say f of c doesn't exist. Now, technically, I have seen some really weird situations where the limit doesn't exist, but the function does with these kinds of situations. You don't have to write this, but just kind of store it up in your mind. So in this case, let's say it looks like this. Well, the left-sided limit is positive infinity. The right-sided limit actually equals something, but still the left and the right don't match, so the limit still doesn't exist. But there is a solid dot there in that case, so we could say the function does exist. So I've seen some weird situations like that, but for the most part, the function doesn't exist either when you have a vertical asymptote. But just to be safe, we'll just say the limit does not exist. Okay? And then there's one more case. Oh, actually, nope, never mind. I think that's it. Those are all the situations where a limit would fail to exist. So you have two types of removable discontinuities and two types of non-removable ones. Now, we have the oscillation ones that we talked about before, but I guess we can add it, but it's kind of like I said, it's so rare. But we'll add it just for the heck of it. Do your best to draw something like that. But in those cases, we would say that the limit doesn't exist. That's all you have to say there. Pretty simple. Matter of fact, for all three of these ones, you could just say the limit doesn't exist. Even for that first one that I put up earlier, where I said the limit from the left and the right don't match, really, instead of saying this, you could just say the limit doesn't exist there too. I just like this answer better because it's more specific. It actually gives a specific reason why the limit doesn't exist. But technically, that's your answer for all of them. Over here, you have to be a little bit more creative, but there it is. All right, so FRQ tip. It's a really common FRQ type question to determine if a function is continuous or not at a given value, x equals c. So to properly show your work, you need to do three things. First of all, you need to show that the function exists. So you should be able to plug the number into the function and actually get an answer out of it. Second, you should be able to show that the limit exists. And we're going to talk about a bunch of ways to find limits in our lesson today. But a lot of times these questions are for piecewise functions, so I'll just say that here. If you have a piecewise function, the way you do it is you do the limit from the left and the right, and you make sure they're the same. So we want to find out that the function exists, then we want to find the left and right-hand limits, and then we want to make sure that those two things match. And then that says step 3, but it should say step 2. Let me fix that. So you want to make sure that your answer from step 1 matches your answer from step 2. And if you've done that, then you have come up with enough information to show that, yes, my function exists, yes, the limit exists, and those two things are the same. Okay, now back when we did this lesson, a lot of you guys, when you wrote your answers, you actually did put the letter C here, and I just want you guys to know that's just a variable I'm putting there. There's usually going to be a number there, right? We're trying to show that the function exists at some specific number, like maybe it's 1 or -3 or something like that. Okay, so don't put the C in your explanation. Actually use the X value that they give you. All right, let's go ahead and talk about infinite limits versus limits at infinity here. All right, we've already mentioned infinite limits a little bit. Infinite limits are limits where whenever x is approaching some number, the y value shoots up into positive infinity or it shoots down into negative infinity. Okay, and so like I said, those things are usually associated with vertical asymptotes. Okay, it could look like that, or they could both be going the same way, like maybe they're both going in an upward direction, or maybe they're both going in a downward direction. In this case, you would say that the limit is negative infinity, and in this case, you'd say it's positive infinity, and for the middle case, we would just say it just doesn't exist because they're opposites. Okay, and I don't want you guys to be confused here. Just because I say infinity, that doesn't mean the limit exists. If the limit is infinity, that means the limit does not exist. It's just that if they're both going in the same direction, we could be more specific rather than just saying it doesn't exist, and we could say that it's infinity. Okay, so these things, as you guys can see, are associated with vertical asymptotes. Might want to put a little note there, vertical asymptotes. Limits at infinity are a little bit different. In this case, it's the y values that are infinity, but for limits at infinity, it's the x is approaching positive or negative infinity. And basically what this tells you is it just tells you what's happening on the left or right end of your graph. I'll say, what is y? So what is the y value at the right and left end of the graph? So let me explain that a little bit. Let's say that I had a function that looked like this. Maybe it goes like this, and then it comes up and gets flat over here. Okay. And let's just say we can assume it's just gonna stay flat on this side like that. And over here, we can assume it's just gonna keep going up. So on the left side, it's going up, and on the right side, it's flat. Okay, so for the right side here, that's on the right side of my graph, and that's as x is approaching positive infinity. And so for that case, we would say that the limit is 3. That's the y value. The height of my function at that point. That arrow is at a height of y equals 3. Whereas on the left side of my graph, that's the limit as x is approaching negative infinity. In other words, what's happening on the left side of my graph. And in that case, it's just going up into positive infinity. So this is a limit at infinity that gives us an infinite limit. So infinite limits are where the y value is infinity. Limits at infinity are where the x is approaching infinity. Okay. A lot of times these ones are associated with horizontal asymptotes, like this one that I drew here. The function's getting flat up against this horizontal line. So these ones are a lot of times are associated with horizontal asymptotes. They don't have to, like I showed you on the left side of my graph, but there's no asymptote, it's just going up forever. But on the right side of my graph, it is getting flat up against a line, and that would be my horizontal asymptote. So that's what limits at infinity are and infinite limits are, and the difference between them. One has to do with vertical asymptotes, one has to do with horizontal asymptotes. One has to do with the y values approaching infinity, the other one has to do with x values approaching infinity. So that is comparing and contrasting infinite limits with limits at infinity. And that brings us to rational functions. A lot of the questions that you'll see on our worksheets this week have to do with these. rational functions kind of have interesting answers that have to do with infinite limits and limits at infinity. So let's explore that a little bit. So a lot of times rational functions will have horizontal asymptotes. Okay, you can find the horizontal asymptote of a rational function by finding the limit at infinity. So what do I mean by that? For example, to find the horizontal asymptote of this function here, what I would do is I would find the limit as x approaches positive infinity and negative infinity. Now, we haven't reviewed how to do that yet, but you'll see it a little bit later on in this lesson today. But basically, the answer for this would come out to be 1/2, all right? But you would find the limit at positive infinity, negative infinity, and that would be your horizontal asymptote. Now, just so you guys know, that means that if I were to graph this, like let's say this is 1, I have no idea what the rest of this function looks like, but I do know that on the right side and on the left side of my graph, it's getting flat at x equals 1/2. I'm sorry, y equals 1/2. Okay? I have no idea what the graph looks like in the middle, but it doesn't really matter. All I know is that the left end and the right end are getting flat at y equals 1/2. Okay, so just to recap here then, you can find the horizontal asymptote of a rational function by finding the limit at infinity. In other words, letting x approach infinity. And we'll review that later on in the class. Another thing you can do is you could find the discontinuities of a rational function by finding where the denominator equals 0. If it's a removable discontinuity, then it's a whole. If it's a non-removable discontinuity, then it's an infinite limit. So let me show you what I mean by that. So take this situation here. In this case, we have two discontinuities. The denominator equals 0 when x equals 1 or -1. If I plug in 1 for this one, I get 0. Or if I plug in -1 for this one, I get 0. Either way, we have 0 times something else over here, and that ends up making the denominator equal to 0. So we have two discontinuities. One of them is 1, and one of them is -1. Okay? So we have 1 and -1 as my two discontinuities. Now, the positive one is a removable discontinuity because these cancel out. When that happens, you end up with a hole. So if you were graphing this, at x equals 1, you would have a hole in the graph. But for this one, that's not a removable one. That x plus 1 does not cancel out. And so for those ones, you end up with infinite limits. So at -1, we would end up having either a positive infinity situation or a negative infinity situation with a vertical asymptote. Okay, so let's recap that. You can find the discontinuities of a rational function by finding where the denominator equals 0. If it's a removable discontinuity, like this one, then you end up with a hole. If it's a non-removable discontinuity, like this one, like it doesn't cancel out, then you end up with a vertical asymptote, and it's an infinite limit. All right, so there's our summary. You can find the horizontal asymptote by finding the limit at infinity, and you can find the discontinuities by finding where the denominators equal 0. Okay, so those are common questions that I've noticed that you'll probably see sometime this week in our work for the week. All right, let's talk about properties of limits. So these words are not important over here. They're kind of just irritating, honestly. I'm not going to quiz you on vocabulary or anything. But let's just say you wanted to find the limit of some function that's being multiplied by a number b. Well, basically, you can find the limit of the function first and then multiply that by b. So in other words, if you have a function times b, then just apply the limit to the function, just multiply the b at the end. Okay, so that's it for that one. Let's take a look at another rule, the sum or difference rule. Let's say you want to take the limit of two things that are being added together. Well, the way that you do that is just by taking the limit of each one separately and then adding those results together. So it's kind of like you just distribute it. in a sense. Or the product rule, well, guess what? It does the same thing. So a lot of these rules really aren't all that impressive. If you're taking the limit of two things that are being multiplied together, you could take the limit of each one separately and then multiply them together. And the same thing applies for division. If you were taking the limit of two things that are being divided, well, basically you could just take the limit of the top one and the limit of the bottom one separately and then divide them. Or if you're taking the limit of something that's being raised to a power, well, in that case, just find the limit of that function and then raise that to the power. This one I think is the most interesting one, though. This is the one that's not the most obvious. It's a composition. A composition is where you have a function being plugged into another function. When you're taking the limit of one of these kinds of situations, you're going to apply the limit to the inside function. Okay? And whatever you get as a result, that's what you're going to plug in to the f function. All right? So we'll see some examples of that in our work this week. So, something that we use quite frequently in this class, I mean, it's not like every lesson or anything, but it does show up in almost every unit that we've done, is absolute value equations. And they don't play nicely with calculus, so we do want to know how to change them into piecewise functions. That way, we can actually do our calculus with them. Okay, so suppose I had something like this. This is just an example. F of x is equal to the absolute value of x minus 3. Okay, well, the first thing you're going to do is you're going to set the expression and the absolute value equal to 0 and solve. So x minus 3 equals 0. I'm going to solve, and I end up with x equals 3. The next thing I'm going to do is I'm going to do a number line test. Okay, so I would put the 3 over here. And what I'm going to do now is I'm going to plug some numbers in to the left and to the right of 3 into this expression here. So let's go ahead and plug some numbers in. Let's pick a number less than 3, like let's say 2. 2 minus 3 is negative 1, and the absolute value of negative 1 is 1. Let's pick a number bigger than 3 and plug that in. 4 minus 3 is 1, and the absolute value of 1 is 1. Now, which one of these changed the sign? In this case, the absolute value changed it from a negative into a positive 1, and so we had a change. So that means for all x less than 3, we change the sign. And for all x greater than 3, we do not change the sign. And so the third step, I didn't write it out in words, but what you would do is you would write out your absolute value function twice, but without the absolute value bars. You're going to do one where x is less than 3, one where x is greater than 3, and go ahead and put an equal bar in one of them. It doesn't matter which. We decided that for x less than 3, we changed the sign, so for that function, we're going to make both signs opposite. And that's it. Okay, so now that is how you can change an absolute value function into a piecewise function. That's something that we actually do. We do it for limits, we do it for derivatives, and we also do it for integrals. And so it's just something that you want to make sure you know how to do. It'll come up. All right, so let's talk about how to actually find limits now. There's a lot to it. There's a lot of different strategies, and knowing which strategy to use is a very helpful skill. So let's say you want to find the limit of some function as x approaches c. The first thing you want to do is try direct substitution first. That means just literally take whatever number is right here and plug it into the function. Okay? If you could plug it in and actually just get an answer, well, guess what? That's your answer. Okay? If you can plug it in and get an answer, that means the function exists there, and therefore it must be continuous at that point. And if it's continuous, then the limit is equal to the function's value, and therefore it's just the same thing as plugging it in. So direct substitution is always a good place to start. You may end up having one question like that. Sometimes they give you one, it's really nice, but more often than not, that's not going to work. So if that fails, you have to look at what kind of function you have after that. If you have a polynomial, you have two ways that you could find the limit. One way is by factoring, and the other way is by doing L'Hopital's rule. Now, I'm not going to spend a lot of time reviewing these strategies with you, but I will say that if you go on to the next few slides, I have some worked out examples just to refresh your memory. So how you can use factoring to find a limit, and also how you can use L'Hopital's rule to find a limit. All right, but if it's a polynomial, these are your two options. Now, if you have a rational function, you basically just need to simplify it. And there's an example for that too. Next, we have, matter of fact, I think I'm going to change the wording on this. This should say complex fraction. Let me change that. It is a rational function, but I'm going to change the word complex fraction. That means you have a fraction inside of a fraction. I'll try to change this on your guys' worksheet so you don't have to, but anyway, it should say complex fraction. In those cases, all you have to do is simplify it, and then after that, you should be able to find the limit pretty well. Next, if it's a rational function with radicals in it, we're going to do something called rationalize. Once again, there's an example provided in the notes here, so I'll let you look at it. If you have a log, exponential, or trigonometric function, we're just going to use L'Hopital's rule. And if it's a piecewise or absolute value function, then what you do is you find the limit from the left and right-handed sides, and you hope that they match. If they match, then the limit exists. If they don't match, then the limit doesn't exist. So if all of those methods fail, like if you can't do this, this, or this, and get an actual answer out of it, well, that probably means that it's a non-removable discontinuity. And in that case, what you're going to do is we want to decide, okay, so it's non-removable, which means that the limit doesn't exist. So the answer is either infinity, negative infinity, or it just doesn't exist. And so what we're going to do is we're going to plug numbers in that are really close to the number that we're trying to find the limit of. But you don't want to plug those numbers in exactly. And then you're going to look at the outcome. If you plug in a number really close to C, do you get an answer that's huge? If so, then it's infinity. Or if you plug in a number really close to C, do you end up getting a y value that's really negative? In that case, it's probably negative infinity. Okay, and you have to do it for the right and the left side. If they don't match, then it just doesn't exist. Once again, there's some steps for that in the notes. So I'm not going to go through these with you guys. I'm just going to show them to you. But here's the factoring method one. Here's the rationalizing method one. Here's the simplifying complex fractions method. Here's L'Hopital's rule. And then here's how to work with infinite limits. Okay, so those are all things just to kind of keep in mind. Now, anytime you're doing a limit where, like this, for instance, where you're plugging in infinity for x, a limit at infinity, anytime you have one of those, this is going to be kind of a helpful sheet to look at. Because you might end up, after you plug, your first step is direct substitution. So when you plug it in, you might end up getting something where you have infinity plus a number. And in that case, the answer is just infinity. If you take infinity and you add something to it, you just get infinity. Or if you have infinity and you subtract something, you just get infinity. Okay, so we've done this before in this class, and I'll let you guys look at this. Most of these are pretty self-explanatory. They actually just make sense. Like if you have negative infinity and you subtract infinity from it, you just still have negative infinity. Some of them don't make sense though, so like this one I think is pretty unclear. Matter of fact, this could be plus or minus, but if you have a number being divided by infinity, that equals 0. Okay, that one in my opinion is not very obvious, so that one's worth taking note of. With trigonometry, if you're ever taking the limit of some trig function, like let's say it's sine, well, trig functions wiggle. They go up and down. In other words, they oscillate. And so if you're finding the limit at infinity, remember, this is for infinity, right? This is not for a number. Trig functions can have limits at a number, but at infinity, they won't ever have an answer. They oscillate. They just, as you go farther and farther to right, they never just settle down at one y value. They just constantly go up and down. So no matter how far you go to the right, they'll never get flat at some specific y value. They'll always wiggle, and so they don't have a limit at infinity. Okay, so there it is. Sometimes you'll have trig functions that are written as fractions, so you might end up getting an infinity on the top and an oscillation on the bottom. In that case, the limit doesn't exist, it oscillates. But if you have your oscillation on the top and an infinity on the bottom, then it equals 0. But that only applies to functions that are oscillating because of sine and cosine. So this is just a review. You guys might feel like your head's spinning from all of this information right now, but we'll be practicing this stuff in class and it'll all come back to you hopefully. Here's another slide for you guys about the limits of E and ln. This is something else to keep in mind. I put the graphs here because I think the best way to understand this stuff is with a graph. If you're finding the limit of e to the x, you're plugging in infinity here. Well, e to the infinity power, not surprisingly, is just infinity, but you could see it on the graph. This means the right side of my graph, and on the right side of my graph, it's going up. So the y value is getting bigger and bigger, therefore it's infinity. But on the left side of my graph, it's getting flat up against the y value 0. And so it actually has a y value of 0. Now another way you could do this instead of looking at a graph is just plug it in. If you have e to the negative infinity, negative exponents just move things to the denominator. And as we've already said, e to the infinity is infinity. And as I told you in the last slide, anytime you've got a number over infinity, the answer is 0. So that's another way you could solve this without the graph. It's just by plugging it in and evaluating it. But the picture makes sense. Now for ln, it can get a little bit more confusing, so I think the picture is really the most helpful thing. But at infinity, in other words, on the right side of my graph, it is going in an upward direction, very slowly. It almost looks flat, but it's not. It does get higher and higher and higher forever. And so the limit of an ln function at infinity is infinity. Now, I'm not going to put infinity here, and the reason for that is because ln functions don't go to the left forever. They have a vertical asymptote that they have to stop at. So for this particular ln function, for instance, it's stopping at 0. So as I approach 0 from the right, you can see clearly that the y value is going lower and lower. So the y value is negative infinity. So I think the picture is definitely very helpful when it comes to ln. The final topic for this little review lesson here is to talk to you guys about the intermediate value theorem. Basically, here's what this theorem says. It says, suppose that we have a function that's continuous on the interval from a to b. So let's say it starts here, maybe it wiggles a little bit and it lands over here at b. It doesn't really matter, okay? But it has to be continuous on the interval a to b. Now, the y value that goes with the a, as we'll call that f of a, and the y value that goes with b, we'll call that f of b. Well, according to the mean value theorem, whatever this y value is and this y value is, pick any y value you want to between them, okay? So let's say it's right here and we'll call it k. Well, that means that that y value, if you follow it over on your graph, has to have a point on the graph such that there is an x value, we'll call it c, between a and b. Okay? That's what the intermediate value theorem says. Now, in a more of an Englishy way of saying, a little bit more common sense way of understanding it is, it says that if you go from point A to point B, so long as your line is continuous, you're going to have to cross some number that's between point A and B. That's basically what it's saying. So let's go ahead and read this. This is how you'll usually write your answers to these types of questions if they're giving you like an FRQ type situation. But all this theorem does is it just promises us that there is some value c such that when you plug it into your function, you get some specific k value between your other two y values. Okay, so the first thing you're going to do is you're going to make sure that your function is continuous on AB. How do you do that? Well, discontinuities. I gave you guys a little sheet a while back in lesson 3.2, I think it was, that talks about the continuity of various functions. I think we're pretty familiar with it already, but you can definitely look at it if you want to. But you just want to make sure that your function is continuous on the interval. Next, you want to find out what the y values are that go with these x values by plugging them in. Then you want to make sure that the k value that they're asking about is actually between the two y values you just found in step 2. If it is, then we've got our conclusion. We could say that since f is continuous and it goes from f of a to f of b on the interval a to b, there must be some value c such that f of c equals k. Okay, so that's a really common question. Well, it's not really common, but it comes up once in a while. But that's it. So I think that will conclude our review of limits, and hopefully that was helpful. And we'll put some of this knowledge to use as we practice it this week. So we'll see you guys in class. Till then, have a good one.